Hello, so today we'll be going over the Michaelis-Menten equation. So this is an important model as it describes enzyme kinetics. It relates the reaction rate of the enzyme by the substrate concentrations. Important variables in here would be Vmax and Km, which we'll go into further detail later on in this video. So what we'll want to do is derive this equation, and to do this, we'll first start off by looking at the overall reaction that's going on. So what we see happening is that the enzyme and substrate is turning into its product, enzyme, and the final product of the substrate. But it's also going through this transition state, the enzyme-substrate complex. So if we notice, there's a forward reaction going to the enzyme-substrate complex, which we'll refer to as K1. But there's also a reverse reaction as it goes back towards the reactants. So it would be K minus 1. From the enzyme-substrate complex to products, we'll refer to this as K2. And you can see there's no reverse reaction. There actually is one going on, but it's so negligible that we'll just look at this in terms of a one-way forward reaction. So to begin with, we'll want to then look at the concentration change of the enzyme-substrate complex, which we denote as d times es over change of time. Okay, so the thing is that the change in concentration of enzyme-substrate complex is actually 0. And why is that? Well, that's because there's the complex being made in the forward reaction of K1 reaction, but it's also being depleted as it goes back towards the reactants and as it goes forward towards the products. So let's write that out. We have K1 times enzyme concentration and substrate concentration minus, as it is being depleted, K minus 1 enzyme substrate minus K2 enzyme substrate. Alright, so good so far? Okay, so to continue as we derive this, we'll want to consider the total enzyme concentration. Okay? So this is a sum of the unbound plus bound enzyme. Unbound would be referred to as the enzyme at the reactant side of the reaction and the product side of the reaction. So the concentration of enzyme, E, plus the bound, which would be the enzyme substrate complex, and this gives us our total enzyme concentration. Now this would be considered one of our four main equations for the Michaelis-Menten equation. And to move forward, we'll want to isolate E right here, the enzyme concentration. So as we do that, we get total enzyme concentration minus enzyme substrate concentration. And from here, we could substitute this back into our original equation so that we can proceed. And in doing so, let's see, we'll just say 0 is equal to K1 times concentration in total enzyme minus substrate enzyme times the substrate minus K minus 1 K minus K2. Alright. Oh, there we go. Okay. So, as we continue with that same reaction, we'll want to then distribute out the substrate concentration S. Okay, so this would be K1 total enzyme S minus K1 ES minus K minus 1 there we go. Alright. Cool. Okay, so from here, we'll want to then isolate ES and move this over to one side of the equation. So what would this look like? Well, it would look like this. ES times K1 times substrate concentration plus K minus 1 plus K2. Okay? And that's one side of the equation, which is equal to K1 times total enzyme concentration times substrate concentration. Alrighty. So from here, we'll want to isolate the enzyme substrate concentration to one side, so we'll divide all of this from here. So as we do that, what this would look like is this right here. So we're getting pretty close now to our final equation. But to do so, we need to divide the numerator and the denominator by K1. Okay? So what this does for us is it removes K1 from up here, and as a result, what we should get is total enzyme concentration times substrate concentration over substrate concentration plus K minus 1 plus K2 divided by that K1, right? Oh, there we go. Alright, so if we refer back to the Michaelis-Menten equation, we see that this involves the enzyme reaction rate, which would be referred to as velocity, V naught. Okay? V naught, which for this, we're observing the change in the product that's being formed over time. Okay? And because this is product being formed, we'll be looking at K2 reaction rate times concentration of enzyme substrate. Now, what we can do here is that we can take this equation that we have derived down and plug it in. Now, in doing so, what we get is that V naught is equal to K2 times total enzyme concentration times S over concentration of S plus K minus 1 plus K2 over K1. Okay. Now, looking at this equation, we could take a look at what's going on here. So this is important. Why? Because this is referred to as Vmax. Vmax, well, in order to understand Vmax, let's take a look at K2. So K2, sometimes referred to as Kcat, is the turnover number. So what this means is that it is the number of substrate molecules that a single enzyme can convert per unit of time, which for example could be seconds, So again, this is in reference to a single enzyme. Now, if we consider this in reference to the total enzyme concentration that we have, what we're looking at overall is Vmax, which then is the maximum number of S molecules that all enzymes can convert into product per unit time. So this is when all the enzymes are fully saturated with substrate. Okay, so that's Vmax, which is K2 times total enzyme concentration. But what we also have going on here, this right here, we'll refer to as Km. Okay, so let's go into a little bit of detail about Km, but first let's just clean this up a bit. And cleaning it up, what we actually end up getting is the Michaelis-Menten equation, where V naught is equal to Vmax times substrate concentration, Km plus substrate concentration. So, Km, now what's the importance of Km? Well, if we consider if the Km is equal to the substrate concentration, if they're both equal, what happens is that Vmax, the substrate concentrations will cancel out. Oh, there we go, sorry. So that all we're left with is that velocity is equal to half Vmax. So essentially what Km is that Km is the substrate concentration that we need to have half the maximum velocity. Alright, so what does Km tell us? Well, Km, if we consider if it is small, what it tells us is that we need a small amount of substrate concentration, okay, in order to reach that half Vmax. So as a result, that tells us that our enzyme has a high affinity for that substrate. Now conversely, if Km is high for a given reaction, then that means that we actually need a lot of substrate concentration in order for the enzyme to bind to it and get to half Vmax. So what we say is that the enzyme has a low affinity. Okay. So if we look back again, there were 4 important equations that we referred to. So the first one, obviously, was the Michaelis-Menten equation. The second one being Km. The third one in reference to Vmax. And the fourth one, right here, in reference to total enzyme concentration.